Good evening, everyone. My name is Sheikh Numan Mehdi. I am a full-time research fellow working under Dr. Thanun Sakinzai. So today in this session, we will discuss about the fracture mechanics. This is the flow of content. First, we will discuss the introduction, like the basic terminologies of fracture and also the type of modes of failures in fracture. Then we will discuss the concrete and its mixed design. Then we will discuss about the evaluation of prism of some specific size to determine the fracture toughness and fracture energy and also modulus of rupture or the flexural strength. Coming to the introduction of fracture mechanics, first we have to understand the fracture. Fracture means a breaking of any material into two or more pieces when we apply the load or the stress onto it. So the fracture means a failure of material which starts with the internal irregularities. First, like for example, for instance, if you take this, if I apply the load, then first it will break in its internal irregularities. Irregularities means it will be unstable internally. Then it will appear on the outer surface. So first it will form internal irregularities like holes, cavities, or cracks inside. Then it will appear in the outside, as you can see in this picture. This is the scanning electron microscopy of concrete, where you can see the crack formations here internally. Then it will reach to the surface, outer surface like this, as you have seen in many buildings, they will have this kind of appearance. First, the crack will appear internally, then it will appear at the outside surface. Basically, there are two types of fracture. One is ductile fracture and another one is the brittle fracture. The ductile fracture is the one which applies only to the steel or any metal kind of materials. And the brittle is the one which applies to the brittle materials like concrete, glass, wood. So the difference between the ductile and brittle is, in ductile material, when you apply the load to any steel, like for example, consider this as a steel material. So when I just push from the two ways, and then it will start breaking at the center. Slowly it will deform the shape. Slowly it will change the shape, as you can see in this picture. And then it will break into two pieces. Like I said, the fracture will form by the internal irregularities. Here is the cavities. Then it forms a major cavity. Then the rupture, it will appear in the outside surface and it will break instantly. Like here is the shear failure. You can see the example here also for the screw, for the bolt. The deformation is occurred here when we apply the load at these two ends. And after reaching the maximum load, it will break into two pieces like this by making the shape, the shear shape or the fibrous shape, we can call it as. So this ductile material is only applicable for the steel or any metal kind of materials, as I said before. Coming to the brittle material is the one which does not change its shape, but it will instantly break after reaching the maximum load. For example, consider this as a brittle material. When I apply the load, it will break by forming the internal irregularities. It will break. It will not deform the shape. It will break instantly. So after reaching the maximum load. So here we can see consider this as a material, and there is some notch or any means some internal irregularities in it. When you apply the load, it will form a crack and it will break instantly. So it will be kind of concrete or glass or wood. So with this idea, we can predict that the fracture strength, means the crack formation is more, or the stress intensity factor is more in the ductile materials rather than the brittle materials. So coming to the fracture mechanics, it is, like I said, in this picture, we have understood the cracks, the formation of cracks internally. So fracture mechanics is the study of cracks, or the formation of cracks, or the propagation of cracks. So fracture mechanics is the field of mechanics concerned with the study of the propagation of cracks in materials. So this was developed by the Arnold Griffith, who is an UK-based engineer who developed this terminology in the year 1913. So the fracture involves a crack of some length, the length of which increases upon loading. See, for example, if you consider this, I'm applying with my two hands. Consider this as a load from the top and the bottom. If I apply this, then some crack will develop here, some fracture will develop here. So of some length, some thickness. So this concept brought by the Arnold Griffith. So as a civil engineer, we have to understand, like in the building structures or in any type of a structure, where the cracks will form. So for instance, consider this is a building and we can see the cracks, and many of you have seen in buildings too, the formation of cracks near the beams, near the columns, at the center, at the corners, in the slabs, in the walls. So for example, if you just consider this part, the beam part, the crack is less initially. When the loading happens, means like when the loading continues, the dead load or live load continues, the propagation of crack will be more, depending on the age of the loading, depending on the age of the building, or depending on the instant loading. So formation of cracks in the concrete beam will be like this. It will be small, and as it carries the load, the crack propagation will be more and it appears. So this is one important concern, the size effect. Here you can see when the specimen is small, or when the specimen is small, the crack formation will take at the maximum load. When the specimen is large, it is very easy to take the crack in it. So for example, this we call it as a size effect. So here, as the load increases, for the larger specimens, it will show the minimum deflection, and also the flexural strength as less as the specimen is large. If you consider this larger specimen, it will break with a less flexural strength. When the size of the specimen gets lower, and for the small specimens, even the flexural stress is high, and also the deflection is high at the fracture point. So this we called it as a size effect. As the size of the specimen is less, more will be the flexural strength. There are three modes of fracture. First is mode 1, which donates the symmetric loading, which we call it as a symmetric opening, or the opening or the tension mode. So this is the mode 1, where the crack will happen in a symmetrical way. If the crack appears, it will divide into two equal positions. So that we call it as a symmetric opening, as you can see in this picture. So if the crack appears, it will divide into two equal parts, as you have seen. I think you have seen in many structures like this. This is the mode 1, which we called it as asymmetric opening. Then the mode 2, which we denotes as a antisymmetric separation, but in plane shear mode, which means it will be in the some plane, means like this. It will be in some plane, it will be in plane, it is in the same plane, but it will shear. It will shear either like this, or like this, or back, or forward, as you can see in this picture. So it is in the same plane, but in the shear. It is in the same plane, but in the shear. This is the mode 2. The mode 3 is the one which donates the antisymmetry separation, but not in plane. It is out of plane. Means it is of same plane, but not in plane, but out of plane. So this is the example. In structures, you can see this kind of out of plane shear failures. So these are the three modes of fracture. And usually this kind of fractures or this kind of crack appearance we will see in buildings. This is the formula to calculate the stress intensity factor. As I said, for the metal kind of materials, the stress intensity factor will be more because it takes a maximum load to make the deform the shape, and also then it will crack. So it will take, obviously it will take more stress when compared to the brittle materials like concrete, glass, or wood. When we apply the load, that will break instantly. So the stress intensity factor will be less for the brittle material, and the stress intensity factor will be more for the ductile material. So this is the formula where this is the stress. For example, consider this: when we apply the load here, the hands, what I am using is the stress, which is in megapascal or Newton per mm square. Then it will form some kind of crack because of pull out stress, and this, the crack length which appeared here, is, we call it as A, we donate it as A, and W is the total width of the specimen, and L is the total length of the specimen. So this is the formula: sigma F root of pi A. F is the function of geometry and the crack length. That means the width by the length ratio divided by how much crack appeared here. So that length. So F we can calculate by that. And it is also called it as fracture toughness value. Means this formula, the stress intensity factor, is also called it as a fracture toughness value. And the unit is, as I said, here it is sigma. So the stress, which is in Newton per mm square, which we call it as megapascals, MPa, and root pi A. A is the crack length, which is in meters, and root of meters is meter and a half. So the unit of the fracture toughness values is MPa, meter and a half. So as I said before, the fracture toughness values for the ductile materials, the steel kind of materials, like here we have medium carbon steel, pressure vessel steel, hardened steel, aluminum, titanium, copper, lead. So these are the ductile materials, and they have the stress intensity or the fracture toughness value is more compared to the brittle materials like glass, hardened cement paste, concrete, nylon. So they have less than one in glass, in cement paste, and also in concrete. But nylon, since it is a fabric kind of material, so it will have little more compared to above these materials. So, but steel materials like metals have more stress intensity or the fracture toughness values because it deformed its shape, then it will break. But the brittle material will break instantly when it reaches to the maximum load. So that is the part of the introduction to the fracture mechanics. Now we will come to the concrete mixed design, concrete and its mixed design. So basically, concrete is the material which we use in every structure to build houses, to build any kind of structure, which is the second most used material after water. So the ingredients of concrete is the cement, aggregates, water. Aggregates will be in gravel and also in sand. So cement, aggregates and water with will make the concrete. So the gravel, the coarse aggregate, we have in the aggregates, we have two different types. One is the coarse aggregate, which we called it as a gravel, and the fine aggregate, which we called it as a sand. So when you take this, the gravel should cover almost 40%, then the sand should cover 25%. The water should be around 15 to 18%, depending on the ratio. Cement should cover 10%, and air content should be around 5 to 6%. Why the air content plays an important role? Because the concrete should set like this in the harden. Without air, it will not set. So we will consider the air content too, just in our terminology. So concrete, when you mix all these things, the wet mix will be like this. Then after setting, the specimen will look like this. So this we have to demonstrate with a prism of specific size in our laboratory to test the concrete and to understand the fracture mode of it. So concrete mixed design is the design which we do for the concrete to make in a proper way, to make the concrete in a proper way of the specified strength. So this is the code book which we use, British Standards 8500-2019, the recent code book, which is used to produce the concrete. The grade of the concrete. The grade of the concrete means it is the strength of the concrete achieving after 1 month approximately, like we consider 28 days. So after 28 days, that grade of the concrete, what we consider in our design, should achieve that much strength. So if you consider C10, C10 is the concrete mix with a 10 MPa of strength, megapascal of strength. After 28 days, we should get 10 MPa when we test in the lab. So similarly, the different grades are there. C15 means 15 MPa, 20 means 20 MPa. Basically, in construction, they will use this as a very basic to construct the buildings in residential buildings. So they will use this 20 to 25 MPa as a basic. Then the higher grades depends on the engineer choice. So C10, C20, C25, C30, C35, C40. Above C40, we call it as a higher grade. And up to C40, we call it as nominal grade. So where C stands for the concrete mix and the number stands for the strength achieved after 28 days of testing. It will be using 150 mmQ we have in our laboratory. When we come to the practical session, I will explain you the specimen which you use for the compressive strength. So water cement ratios, the water we can't calculate, but by considering water cement ratio, we have to calculate water in the mix design. So basically, by experience, the water cement ratio should be minimum of this range, 0.4 to 0.6, to make the nominal grade of concrete. So the process of concrete mix design is, first we will take, as I said, the ingredients are cement, sand, gravel, and water. So first what we will do, we will add cement and sand. We will mix cement and sand. And then we will add the gravel, the coarse aggregates, what we say. For sand, we call it as a fine aggregate. And for gravel, we call it as a coarse aggregate. Then we will mix in this mixer for 3 minutes. The dry mixing, we call it as. Then we will pour water of the calculated quantity. Then we'll mix for another 5 minutes. So total mixing will be for 8 minutes, which is a standard procedure as per the code books. Then final product will be the concrete like this. So as I said, the concrete grade C10, C15, C20, C25, C30, C35, C40. Above C40 is the higher grade. So in our laboratory, we will cast for the C20 grade. And these are the ratios which you have to memorize it. Basic, these are the ratios which we have, which is a thumb rule to keep in mind to make the concrete mix design. So for C10, it is 1:3:6. I will tell you in the next slide what is it. So for C15, it is 1:2:4. Here, basically, it will start with 1, and then the second number you have to remember, and the third number is just a double of that, just a twice of that number. So 1:3:6 is for C10. 1:2:4 is for C15. For C20 is 1:1.5:3. C25 is 1:1:2. C30 is 1:0.75:1.5. C35 is 1:0.5:1. C40 is 1:0.25:0.5. It is not 5, it is 0.5. So the water is calculated by using the water cement ratio, as I said before. So many of you will get a question, what is these ratios? So the ratios, if you consider C20, the ratio is 1:1.5:3. That means the first one is cement, the second one is sand or the fine aggregate, the third one is coarse aggregate or the gravel. So let's take the ingredient in kilos, kg. Cement is 1 kilo. If you consider 1 kilo of cement, we have to add 1.5 kilo of sand, then the gravel of double of that sand. So it's 3 kg. Means 1:1.5:3, cement, sand, and gravel. As I said, water cement ratio, you have to consider 0.4 to 0.6. So here I have taken 0.5 as a basic. Then the water will be multiplication of cement with 0.5 ratio is in kg, because the cement is in kg. So water we have to calculate in kg. If your concrete mix is dry or harsh, then you have to increase the water cement ratio and make it to the workability, the workable concrete. And if your concrete is more fluid, you just reduce the water cement ratio and make it to the workable concrete. We have a specific specimen for it to test, which we called it as a slump flow test, as a basic test, where you can pour this concrete and we will see the workability of concrete. So it is should be under the guideline. It should be with the guidelines of the British standards, what it is mentioned. So that you will understand when you do the practical session. So this is the basic thing where if you get the dry mix, you have to add the water cement ratio and make it to uniformity. And if it is wet mix, then you have to reduce the water cement ratio and make it to the uniformity. So the third part of our session is the experimental evaluation of prisms. So the slide which I showed you before regarding the pull out of the specimen, which is applicable when the stress is applied in the vertical section. But here in laboratory, we will do the testing of the prisms, which is a beam, which has a horizontal alignment, and the load, the 3-point loading on it. So we will select a prism. We call it as a prism, which is of 100 mm by 100 mm by 500 mm. Then we will make the concrete mix based on these grades, C20 or C25. Then we cast in specimen with tamping of 25 blows in 2 layers. That you will get to know in laboratory. Then the 3-point loading setup, we will set up the 3-point loading, like the above load should be at the center, and the bottom supporting supports, the bottom support should be of L by 3 and L by 3 distance from the end phases. So that we will see in the laboratory. And after the application of load, some crack will develop here. Like for example, this is the beam, and if you apply load, then some crack will develop here, and we will measure that crack. And for that, the formula is different. It is different from the previous one, the stress intensity factor, which applied in the vertical application. So that formula is different rather than the prism application. This formula is different because this is 3-point. So the stress intensity factor is P by BD. P is the application of the load. BD is the breadth and the depth, and root of D is the depth, and F alpha is the function of the span to depth ratio. So here we will use this formula to calculate the stress intensity factor, which I will show it later. The fracture energy. The fracture energy is the energy required to develop the fracture, or the energy required to create the unit area of the fracture surface. So which is donated by GF, and this is the formula. GF is equal to 1 upon ligament area, integration of load, and the deflection with the depth. So this is the formula for fracture energy. And the flexural strength for prism is calculated as this formula. Sigma is equal to 3FL by 2 BD square. So F is the maximum force applied, the force which applied on the beam, this one, the point force, and L is the length, B is the breadth, and D is the depth. So this formula is for the flexural strength, which we calculate after the breaking of specimen. So if you see the breaking of a specimen, if the specimen breaks after the application of load, then this formula we use it to calculate the flexural strength. This is the BSEN standard to test the hardened concrete for the flexural strength. BSEN 12390 Part 5 2019. So thank you so much. Now we will move on to the calculation part. So as I said, like fracture toughness, the formula is different. And then the fracture energy, which is correlevant, and the modulus of rupture or the flexural strength. So we will see the calculation of this. So consider the beam of some length with an effective span, and there is some crack of some distance, and there is a load. The load we consider here is 500 kg, but the force to consider in the calculation is in Newton. So you have to multiply that 500 kg into to convert into Newton. We have to multiply the 9.81, the factor of it. So the concrete which is used is 30 MPa, means C30 has been used in this specimen. This is the depth and this is the width of the cross section. So coming to the fracture toughness, Ki is equal to P by Bt, root of D, F alpha. P is the applied load, which is 500 into 9.81 is the factor to convert into Newton. Then the force, then the load converted into force, that is 4905 Newton. D is the depth of the specimen, which we have a 10 centimeter, so it is 100 mm. B is the out of plane thickness, which is 10 centimeter and 100 mm, that is equal to 0.1 meter. Why we are considering this 0.1 meter? Because we have to make a unit of Newton per mm square meter to the power of half. So because the stress intensity, as I described before in the previous slide, like the unit of the stress intensity factor or the fracture toughness value is represented in MPa meter per half or Newton per mm square meter per half. So if you see the calculation, the S is the span, effective span, not the total span, the effective span, because the function of alpha means it depends on the effective span from center to center of the supports. So this is the effective span. So the effective span is 50 centimeters, so convert into mm, 500, and D is the depth, which is 10 centimeter, and divide this, you will get the function of alpha. Just put all these values in the formula and you will get the stress intensity factor or the fracture toughness, which is equal to 1. Why it is equal to 1? Because this is concrete. We are testing for the concrete. So we are testing for the plain concrete. So it should be 1 as per our table. So here you can see it should be 1, the fracture toughness value. So the second is the specific energy, the second calculation, where the maximum energy required to develop the crack. So it depends on the load displacement curve. So as the load increases, the crack form, and at some point, the load try to decrease and come to some displacement, means by making some displacement. Then the maximum force, what we consider is 4905, which is 500, that is 4905. And the displacement, you just consider 20 mm as an example. Then this is the formula for the fracture energy. GF is equal to A by ligament area. Ligament area is the area which covers the the part of the internal cracking, and also the part of the internal cracking is the ligament area. That no, the normal area is, we will just multiply with the length and breadth. So the ligament area means the development of crack which happened here. So we have to consider that too. So we called it as a ligament area. So integration of P del d delta. So where GF is the fracture energy in joule, because it is energy unit is joule per meter square per that area. And the WF is the work of fracture, and LIG is the ligament area. Ligament area is calculated as R minus A. The R is the half of the radius. In circle, how we calculate the radius, the diameter, half of the diameter is equal to the radius. So just for the understanding point of view, you consider that R is half of the specimen, the distance of half of the specimen. So specimen radius, which is 10 centimeter divided by 2 and 0.05 in meters, is the notch length, which means the notch length is 2 centimeter, the crack length. So 2 centimeter, which is equal to 0.02 meter. T is the thickness or the depth. So thickness is 10 centimeter, so 0.1 meter. So put it in the formula, the ligament area is calculated as this. So this ligament area is equal to 3 into e power minus 3 meters square, because we converted all in meters. Then integration of P d delta. Integration of P d delta. Delta is the load line displacement. Means from 0, it deformed and came to 20. So this 20 is the load line displacement. So that is delta. So convert this 20 mm into 20 mm into meters. This is 0.02. This, I think here some error is there. This is 0.02. If you convert 20 divided by 1000, because it is in mm, so divided by 1000, it is 0.02. Integration of 0 to delta, 0 to 0.02, the load into the depth into the delta is 0.02. So you calculate this, then the integration, you do the integration of it, which is 9.81 into the x minus 9.81 into the lower limit. So WF is equal to 9.81 into upper limit minus 9.81 into lower limit, which is equal to this much joules. Therefore, the GF is equal to 1 divided by ALIG. This value we have, ALIG also we have, just calculate that. And this is the fracture energy of the particular specimen in joule per meter square. So this is the unit of the fracture energy. The modulus of rupture or the flexural strength is calculated after the breaking of the specimen, after reaching the maximum load, and also the specimen breaking. So that force, we take it. So this is the maximum load. Consider, for example, this is the maximum load we consider in this specimen, this one, and L is the length of the sample, B is the width of the sample, D is the depth. Just convert everything or just keep it as same, because the strength should be in megapascal or Newton per mm square. So keep the units in mm. So insert all the units in the formula. 3 into F. F is the 4905 into L is the 100 divided by 2 D square. So you calculate this, the flexural strength is 0.795 Newton per mm square. We call it as 0.795 megapascal. So this is all about the basic terminology of the fracture mechanics. So thank you so much.